So this video is going to show you how to solve problems with horizontal projectile motion and give you some insights to some of the variables and how they're connected, related to each other. So we'll do this through an example. The ball rolls horizontally off a table at 3 meters per second. The table is 1.1 meters from the floor. Where would the ball land from the edge of the table? So let's start with the end of this. Where would the ball land at the edge of the table? That's going to be a little bit of vocabulary. So this is the edge of the table, and this is the point where the ball is considered to be a projectile. A projectile is any object that moves through the air without controlling its flight. Parachutes are not a projectile, airplanes are not a projectile, sailplanes are not a projectile, but a ball is a projectile, a football is a projectile, a runner jumping in the air is a projectile, a bird is not a projectile. So this is the point where the ball becomes a projectile, and what I want to know is this horizontal distance where it lands. This horizontal distance has its own name. It's called the range. So anytime a problem asks about the range or mentions anything about the range, it's talking about this horizontal distance down to where the object lands on the ground or lands on its surface. All right, let's look at the other givens that we have. We have 3 meters per second, and I have 1.1 meters from the floor. 3 meters per second, that means the ball is moving this way horizontally. It tells me that. 3 meters per second. It also says the edge of the table is 1.1 meters from the floor. So this distance all the way down is 1.10 meters. Notice the arrows that I have. The velocity is horizontal and the height is vertical, and that's going to become important in terms of figuring out what we have and what we don't have. This is basically a kinematics problem with two lists of givens, one in the horizontal direction and one in the vertical direction. So when I'm solving this, I'll keep them separate. So let's start with our list of givens. I'm going to list all the variables that I know that are in there are kinematics. And to do that, some students came up with an idea a couple of years ago, and they said that we'll just call this Vox TVA. So you're probably thinking, what do you mean, Vox TVA? Well, Vox was our initial velocity, the VOX, T, final velocity, and the acceleration, Vox TVA. And then we'll keep two lists of givens because we have two accelerations. One is the vertical acceleration, and the other one is going to be the horizontal acceleration. So I'll divide this up, simple little table. There we go, horizontal and vertically. So if a variable can point from left to right, that's the horizontal column. If a variable goes up and down, I'm going to call that my vertical column. As I look at my givens, I have 3 meters per second horizontally. And what that means is that I'm not going up or down when I leave the table. So actually that is a given. That's 0. So vertically, I'm not going up or down. That's going to be 0. X is the distance I've traveled, and I'm going to take my starting point up here to be x naught, and my initial x, and that's going to be 0. So the distance I travel is down to the floor. So I'm going to make any time I move down negative. It's going to make the math easy if I just always call that negative. So negative 1.1 meters. What else do I know? Time? No. Velocity when it lands? Vertically? No. Acceleration? Yes. And the acceleration is due to gravity, and it goes down. So I'm going to make that also negative 9.80 meters per second squared. And this idea of acceleration being 9.80 meters per second squared is kind of like the free space in bingo. You're always going to have it. So you can always just write that down vertically. It's negative 9.8 meters per second squared. The only time it wouldn't be negative 9.8 meters per second squared is if you were on another planet, say Mars. If that was the case, the acceleration would be a smaller number. Or maybe the moon, where it's 1.67 meters per second squared. But for all our problems that are on the Earth, automatically it's going to be negative 9.8, so you know that given. Okay, let's look at our horizontal givens. These are all the kinematics givens that are moving from left to right, horizontally. Let's see, if I look at this, the range is one of the variables that I have, so that's going to be my x, but I don't have it. That's actually what I'm looking for, so I'll put a little question mark there. And horizontally, I know the initial velocity is 3 meters per second, so I'll write 3 meters per second. Horizontally, horizontally, the velocity, it's also 3 meters per second, but we're not going to use it. Horizontally, we know that there are no forces acting on it horizontally, and I kind of know that in my real life because I cannot sit on the vertical wall on the side of my room. I can only sit on the floor. So because there's no force moving horizontally, that's going to be 0. In fact, it's always going to be 0. And as it turns out, that's kind of a useless piece of information. So is the horizontal velocity. So horizontally, I really only have three givens that are important: the 3 meters per second, the x, and the t. Now, time is unique. It's a scalar. It doesn't have direction. So if I find the time in, say, the vertical column using vertical givens, it's going to be the same time in horizontal. In other words, the time it takes to fall is the same amount of time it takes for it to move horizontally. So that's why the two times are going to be the same in both columns. They're the only variable that are going to be the same in both columns. So vertically, I have 5 variables: the initial velocity, the displacement, the time, the final velocity, and the acceleration. Horizontally, I only deal with 3 variables: the initial velocity horizontally, the distance horizontally, and the time. All right, so we said it's going to be a kinematics problem. So let's go ahead and list our kinematics equations that we know. X equals x naught plus v naught t plus 1/2 at squared. And v equals v naught plus, at. Let's see, what else do I have? Oh yeah, v squared equals initial velocity squared plus 2ax. And those are our main equations. We also have that x over t is equal to v plus v naught over 2. So I have 4 kinematics equations I can use. Just depends on what I'm given. And when I'm using my equations, I have to get givens from one column or the other. But I cannot cross columns. I can't pick a value from another column just because I need it. So I have to stay in the columns. All right, what else do I know? Well, time is going to be the key variable for a lot of these problems, because if I find the time using one set of givens, I can find the time in the other set of givens. The other thing I know is that because horizontally there's no acceleration, there are a couple equations that I cannot use horizontally. It's horrible too. There we go. Anything with an acceleration in it, the acceleration would go away horizontally. So horizontally, the first equation becomes, let's see, let me undo that. The first equation horizontally becomes x equals x naught, and we're always going to make that 0, plus v naught t. And the acceleration goes away because it's 0 horizontally. Horizontally, the second equation, it doesn't work. It becomes v equals v naught. Horizontally, the third equation doesn't work. It becomes v squared equals v naught squared. And the last equation works, but we're really not going to do anything with it. So I have x equals x naught plus v naught t. And what I know is that x naught is going to be equal to 0. So x is equal to v naught times t. Because it's horizontal motion, I'm actually going to specialize this, and I'm not just going to call it that, but I'm going to say that the range is equal to v naught times t. And this variable up here, that's the range. So whatever variable I get in that spot, I put down in my equation. So horizontally, I only have one equation I can use. I don't have to worry about all those other kinematics equations. All I have is range is equal to the horizontal velocity times time. So remember, that velocity right here is horizontal velocity. Not vertical, but horizontal. All right, let's get back to actually solving the problem. Where will the ball land? So if I want to find the range, I have the velocity in my range equation. That's great. Distance, well, that's actually what I want. And I just noticed that I put the range in the wrong spot. Some of you may notice. I'm sorry about that. The range should be here. That's the range variable. Sorry about that. All right. So I'm looking for the range variable, and I need to know the time. To find the time, well, I can't use any of my horizontal givens, but I can use vertical, because in kinematics, our full-blown kinematics equations, I need 3 variables to find the fourth. So I have the initial velocity, I have x, I want t, and I have the acceleration. So I can use one of my equations on the left. So when I look over there, I need an equation with x and x naught's 0, so that's easy enough. The initial velocity and acceleration and time. So if I look at my equations, that's going to be the top equation. That's going to be the one that I'm after. So let's go for that one. So that's going to be x equals x naught plus v naught t plus 1/2 at squared. All right, a couple things. First off, where I start is always going to be 0, so that's going to go away, and that's at the table. And the initial velocity vertically, oh, nice. That's 0 as well up here, so that's going to go away. That's going to make my equation nice and short. X equals 1/2 acceleration times time squared. And I'm looking for the time. So I'm going to go ahead at this point and just put in my numbers. X is negative 1.10 meters. That equals 1/2 negative 9.80 meters per second squared times time squared. So I multiply both sides by 2. I then divide both sides by negative 9.8. And then I'll square root. And when I do all that work, I get the time to be 0.47738035,415 seconds. So that's the whole number that's displaying on my calculator screen, and that's the whole number I'm going to use in solving this problem. That's not you, it's the bell in my room. All right, let's keep going. So I'm still trying to find the range. I only have one equation I can use to find the range. At this point, I know the time. The time 0.438. So let's write that up here. 0.4738 seconds. 0.4738 seconds. Okay, so that's good. So now, if I'm looking at the horizontal givens only, I can use my range equation. I'm looking for the range. I have the initial velocity horizontally. I have the time in the air. I'm all set. So let's see. The range is equal to v naught horizontally times time. So the range is equal to the initial velocity horizontally. That's going to be 3 meters per second, not 0 because that's vertical, times the time with all those decimals. 0.4738035,415 seconds. And when I do all that, I get my range to be 1.42 meters. So the ball is going to land 1.42 meters away from the edge of the table.